Assalamu alaikum and welcome to lecture number 26 of CS 317 Operating Systems. The topic of this lecture is deadlocks and we are using chapter number 7 of the syllabus charts book for this topic. From the previous lecture, we understood why deadlock prevention is not a good option. We realized how deadlock avoidance better utilizes system resources. We listed the algorithms for deadlock avoidance. We explored the resource allocation graph algorithm. We explored the banker's algorithm. We resume our discussion on deadlock avoidance. Let us continue banker's algorithm. In the previous lecture, we were given a system with allocation, max, and available as shown here. We computed the need matrix. We found that the given state is safe. The safe sequence is P1, P3, P4, P0, and P2. In this safe state, P1 additionally requests one instance of A and two instances of C. This means that the request of P1 or request 1 is 1, 0, 2 because it is not asking for any instance of B. So the question is, can request 1 be granted? Run the resource request algorithm. Request 1 should be less than equal to need 1, which it is. Request 1 is 102 and need of process 1 is 122. So this condition is fulfilled. Request 1 should be less than or equal to available. Request 1 is 102, available is 332. So this condition is also true. Now we assume that we are granting request 1. So available becomes available minus request 1. 332 minus 102. Available becomes 230. Then allocation 1 is allocation 1 plus request 1. Request 1 is 102. Allocation 1 is 200. So the new allocation of process 1 would be 302. And need 1 is need 1 minus request 1. Need 1 is 122. Request 1 is 102. So the new need of process P1 is going to be 020. Now we have changed the system pretending that we are granting request 1. We have taken resources from the available vector, added them to the allocation of process 1 and subtracted them from the need of process 1. We have assumed that request 1 is granted and the state has been changed accordingly. Now we find out if the resulting state is safe. So this is the state that we just created. Run the safety algorithm. Set all finish to false. Set work equal to available. Find an index I such that both finish I is false and need I is less than equal to work. Let's start scanning from P0. P0 does not fulfill these conditions, but P1 does. Need I is less than equal to work. Need 1 is 020 and work is 230. The condition is fulfilled, so work should be work plus allocation 1. Work is 230. Allocation 1 is 302. So the new work will be 532. Then finish 1 is true. Again, find an index I such that both finish I is false and need I is less than equal to work. Continuing is scanning from P1. P2 does not fulfill our requirements, but P3 does. Need 3 is less than equal to work. So work is work plus allocation 3. Work is 532. Allocation 3 is 211. So the new work is 743. And finish 3 is true. Again, we find an index I such that both finish I is false and need I is less than equal to work. Continuing is scanning after P3. P4 fulfills our conditions. Need 4 is less than equal to work. So, work is work plus allocation 4. Work is 743. Allocation 4 is 002. The new work becomes 745 and P4's finish becomes true. Again, we find an index I such that both finish I is false and need I is less than equal to work. We left off at P4, so we loop back to the first row of the matrix and we check P0, which fulfills our conditions. Need 0 is less than equal to work. Then work is work plus allocation 0. Work is 745. Allocation 0 is 010. So the new work will be 755 and finish 0 will become true. Again we find an index I such that both finish I is false and need I is less than equal to work. You can see that the only process that fulfills these conditions is P2. Need 2 is less than equal to work. Need 2 is 600 and work is 755. So work is work plus allocation 2. Work is 755. Allocation 2 is 302. So the new work becomes 1057 and finish 2 becomes true. Look at this matrix. Finish I is true for all I. So the state is safe. The safe sequence is P1, P3, P4, P0 and P2. So this means that request 1 can be granted. This is the new state of the system after grant of request 1. If you go back, you will see that this state was what I received after I ran the resource request algorithm for request 1. In this safe state, P4 additionally requests 3 instances of A and 3 instances of B. That is, request 4 is 330. The question is, can request 4 be granted? Run the resource request algorithm. Request 4 is 330. Need 4 is 431. So request 4 is less than equal to need 4. The first condition is fulfilled. Request 4 is 330. Available is 230. Request 4 is greater than available. P4 is asking for resources that are not free. So request 4 cannot be granted. The system state is unchanged. In this safe state, P0 additionally requests 2 instances of B. So request 0 is 0, 2, 0. Can request 0 be granted? Run the resource request algorithm to see if request 0 can be granted. If it can be granted, Run the safety algorithm to see if the resulting state is safe. If the state is safe, furnish a safe sequence and show the new state after grant of request 0. Homework. Consider a system with 5 processes P0 through P4 and 4 resource types A, B, C and D. Look at the state that is shown here. I have shown the allocation matrix, the maximum matrix and the available vector. The question is the state safe? P1 requests 4 and 2 instances of B and C respectively. Can the request be granted? We continue the topic of deadlocks, but we switch to a third book. We are now referring to chapter 10 of the book by the author Gary Nutt. The subtopic that we are going to talk about is deadlock detection and recovery. Why shift from avoidance? Whereas avoidance algorithms avoid unsafe states, even if the system might recover from them, detection and recovery algorithms ignore the distinction between safe and unsafe states, and the resource managers can allocate units whenever they are available. If processes seem to be blocked on resources for an inordinately long time, the detection algorithm is executed to determine whether the current state is a deadlock. Detection algorithms determine if there is any sequence of transitions in which every process can become unblocked. The cheapest solution to deadlock. Prevention implements policies at design time, which limits resources from being allocated even when they are free. Avoidance grants or denies requests at runtime, which still leads to the situations where free resources are not allocated. However, the problem and its consequences are less severe here than in prevention. Avoidance requires the function of the safety and resource request algorithms in the background throughout system execution, which obviously uses processing time. Detection and recovery does not stop any free resource from being allocated, and no background algorithm is run. The algorithm only starts to work when the system seems inactive for a long time. A revision of resources. Resources have been defined as anything a process needs to proceed. This could be a block of primary memory, a file, or exclusive access to a device. Serially reusable resources are those resources that a process requests the operating system to allocate exclusively. This means that the process asks for the resource and the operating system grants it mutual exclusion on the resource. And the process will later release the resource for another process to reuse. Processes also use consumable resources which cease to exist once used. For example, when a process blocks on a read operation that is attempting to read the next character from a keyboard, then the character is needed by the process in order to proceed. However, once the process acquires the character, it will never release it. So the process will consume the character. Instances of the two resource classes are treated differently by the resource manager and processes and have different theoretical properties with respect to deadlock analysis. Reusable resource graph models. A reusable resource graph is a directed graph such that the following is true. The n plus m nodes represent n processes and m resources. An edge from Pi to Rj is a request edge, which represents a request for 1 unit of Rj by Pi. An edge from Rj to Pi is an assignment edge which represents the allocation of 1 unit of Rj to Pi. For each Rj, there is a count of the number of units of the type Cj that is graphically represented by small tokens inside Rj. The circular weight. This is a reusable resource graph depicting the circular weight. There is only one instance of each resource type which is held by a process indicated by an assignment edge. Each process needs an instance of another resource type indicated by a request edge. A state leading to another. Part A is a system state. Notice that Pi wants an instance of Rk and that instance is free. Part B is a reusable resource graph for a different state that is reached from the one represented in Part A. How? In Part A, Pi was requesting for one instance of Rk, and in Part B, that free instance of Rk has been assigned to Pi. In this figure, Part B, a transition has occurred in which the idle unit of Rk is allocated to Pi. Is Part B a deadlock? State transitions in a reusable resource graph. A state transition occurs whenever one of three events occurs. 1. Any allocated resource is released through the deallocation event D. 2. A new resource is requested via the request event R. 3. A resource is allocated to a process with the allocate event A. Events that change states. Request. Assume the system is in state Si. Pi can request Q units of Rj. Q must be less than equal to Cj. Cj is the total number of instances of reusable resource Rj, provided Pi has no outstanding requests for any resources. Because if Pi has an outstanding request, then Pi must be blocked, and a blocked process cannot request anything. A request causes a state transition from Si to Sj. The reusable resource graph for Sj is created by adding Q request edges from Pi to Rj to the graph of Si. Acquisition. Assume the system is in state Si. Pi can acquire a unit of Rj if and only if there is a request edge from Pi to Rj. An acquisition causes a state transition from Si to Sj. The reusable resource graph for Sj is created by changing the request edge from Pi to Rj to an assignment edge from Rj to Pi. Release. Assume the system is in state Si. Pi can release a unit of Rj if and only if there is an assignment edge from Rj to Pi and there is no request edge from Pi. Because if there is a request edge from Pi, then Pi is blocked and a blocked process cannot release resources. A release causes a state transition from Si to Sj. The reusable resource graph for Sj is created by deleting the assignment edge from Rj to Pi. This is a reusable resource graph. There are two processes, P0 and P1. Resource R has two instances. The state of the system is S0. A request R1 is made by P1 for an instance of R. P1 has no outstanding requests, that is, it is not blocked. A request H is added to S0. The state of the system is S1. A request R0 is made by P0 for an instance of R. P0 has no outstanding requests, that is, it is not blocked. A request edge is added to S1. The state of the system is S2. An allocation A0 is made to P0 of an instance of R. The request edge from P0 to R is removed from S2. An assignment edge is added to S2. The state of the system is S3. An allocation A1 is made to P1 of an instance of R. The request edge from P1 to R is removed from S3. An assignment edge is added to S3. The state of the system is S4. A request R0 is made by P0 for an instance of R. P0 has no outstanding requests, that is, it is not blocked. A request edge is added to S4. The state of the system is S5. A request R1 is made by P1 for an instance of R. P1 has no outstanding requests, that is, it is not blocked. A request edge is added to S5. The state of the system is S6. If you look at P0, it has one request which cannot be fulfilled. It can only be fulfilled if P1 leaves its instance of R. If you look at P1, it has one request which cannot be fulfilled. It can only be fulfilled if P0 leaves its instance of R. This is a deadlock. Knots in the resource allocation graph. There could be a state diagram that contained a knot, and once the system entered any state in the knot, it could never transition to other states outside the knot. In the figure shown here, the system can move from state Sj or Sk into the knot, but then it would never be able to change to any of the states outside the knot. This situation complicates the algorithm that checks the resource allocation graph to see if a process is deadlocked. How to detect a deadlock? To detect if Sk is a deadlock state, we must be assured that there is no sequence of transitions unblocking all blocked processes. We can consider all transformations of the reusable resource graph to determine if there is a new graph reachable from it. If we can find a series of transformations in which a process Pi is unblocked, the original state is not a deadlock. Graph reduction. A graph reduction is a set of transformations representing optimal action by processes. The intent is to decide whether the current state is a deadlock. A serially reusable resource graph can be reduced by Pi if these conditions are met. Pi is not blocked. Pi has no request edges. There are assignment edges directed into Pi. The reduction transforms the reusable resource graph by removing all assignment edges to Pi. Reducibility of a resource allocation graph. A reusable resource graph is irreducible if it cannot be reduced by any process. A reusable resource graph is completely reducible if there is a sequence of reductions that leads to a graph having no edges of any kind. It can be proven that given a reusable resource graph representing state Sk is a deadlock state if and only if the serially reusable resource graph is not completely reducible. The graph of a deadlock state must contain a cycle. A cycle in the reusable graph is a necessary condition for deadlock. However, it is not a sufficient condition for deadlock. Look at the figure shown here. In part A, P0 wants R1. There is one instance of R1 given to P1. P1 wants R0. There is one instance of R0 given to P0. You can clearly see a cycle here. In part B of the figure, P0 wants R1. There are two instances of R1. One is free. The other is given to P1. P1 wants R0. There is one instance of R0 given to P0. You can see the cycle again. There is a deadlock in part A of the figure shown here, but part B is not a deadlock state. Both of them contain the same cycle. Is this reusable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P1 has two requests, one of which cannot be granted, so it is blocked. P2 has a request which cannot be granted, so it is blocked. P0 has a request which can be granted. Reducing the graph by P0. Convert the request edge to an assignment edge. P0 has assignment edges only. P0 releases all its allocated resources. P1 has unblocked. Reducing the graph by P1. Convert the request edges to assignment edges. P1 has assignment edges only. P1 releases all its allocated resources. P2 has unblocked. Reducing the graph by P2. Convert the request edge to an assignment edge. P2 has assignment edges only. P2 releases all its allocated resources. The graph has no edges. We say that the graph has been completely reduced. This shows that the initial serially reusable resource graph did not contain a deadlock. The reduction sequence of this initial resource graph is P0, P1, and then P2. Is this reusable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P0 has a request which cannot be granted, so it is blocked. The same is true for P1 and P2. The graph is not reducible by any process. The given state is a deadlock. Consumable resources. Consumable resources differ from serially reusable resources in that a process may request consumable resources but will never release them. Conversely, a process can release units of a consumable resource without ever acquiring them. What kind of a process will this be? This will be the producer of a consumable resource. Because Such resources may have an unbounded number of units, and because allocated units are not released, the model for analyzing serially reusable resources does not apply to consumable resources. However, by our redefining the model for consumable resources, conditions can be found to test a system state for deadlock. Units of a consumable resource. A consumable resource Rj has an unbounded number of identical units such that the following holds. The number of units of the resource Wj varies. There are one or more producer processes Pp that may increase Wj by releasing units of the resource. Consumer processes Pc decrease Wj by acquiring units of the resource. Consumable resource graph models. A consumable resource graph is a directed graph such that the following is true. The n plus m nodes represent n processes and m resources. An edge from Pi to Rj is a request edge which represents a request for one unit of Rj by Pi. An edge from Rj to Pi is a producer edge which identifies Pi as the producer of Rj. The number of units of Rj is Wj, that is graphically represented by small tokens inside Rj. Events that change states. Request. Assume the system is in state Si. Pi can request any number of units Q of Rj provided Pi has no outstanding requests for any resources. A request causes a state transition from Si to Sj. The consumable resource graph for Sj is created by adding Q request edges from Pi to Rj to the graph for Si. Acquisition. Assume the system is in state Si. Pi can acquire a unit of Rj if and only if there is a request edge from Pi to Rj. An acquisition causes a state transition from Si to Sj. The consumable resource graph for Sj is created by deleting the request edge from Pi to Rj and by decrementing Wj. Release. Assume the system is in state Si. Pi can release units of Rj if and only if there is a producer edge from Rj to Pi and there is no request edge from Pi. A release causes a state transition from Si to Sj. The consumable resource graph for Sj is created by incrementing Wj. This is a consumable resource graph. There are two processes P0 and P1. P1 is the producer of R. Resource R has no instances as it has not yet been produced. P1 is not blocked. P1 produces an instance of R. P0 requests two instances of R. P0 is blocked now. P1 produces three instances of R. P0 is granted its requests. Notice that two tokens have been decremented in R. The system is not deadlocked. Graph reduction. A graph reduction is a set of transformations representing optimal action by processes. The intent is to decide whether the current state is a deadlock. A consumable resource graph can be reduced by Pi if Pi is not blocked. The reduction transforms the consumable resource graph by removing request edges of Pi and decrementing Wj once for each request edge from Pi to Rj. If there is a producer edge from a resource Rj to Pi, the reduction releases an unbounded number of units of Rj and deletes the producer edge Rj to Pi from the graph. Instead of small tokens, we show the symbol of infinity inside the node Rj. Is this consumable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P naught has a request which cannot be granted, so it is blocked. So is P1. The graph is not reducible by any process. The given state is a deadlock. Is this consumable resource graph deadlocked? To answer this question, we attempt to reduce the given graph. Identify the blocked processes. P1 has a request which cannot be granted, so it is blocked. P0 has a request which can be granted. Reducing the graph by P0. Remove the request edge, decrementing an instance of R1. Being the producer of R0, P0 produces infinite instances of R0. The producer edge is removed. P1 has unblocked. Reducing the graph by P1. Remove the request edge, decrementing an instance of R0. Infinity has not changed because infinity minus 1 is also infinity. Being the producer of R1, P1 produces infinite instances of R1. The producer edge is removed. The graph has no edges. We say that the graph has been completely reduced. This shows that the initial consumable resource graph did not contain a deadlock, and the initial consumable resource graph can be reduced with this sequence P0, then P1. Discontinuing our discussion here, let us look at the lessons we learned from this lecture. We covered more examples of the banker's algorithm. We realized that deadlock avoidance was still more expensive than detection and recovery. We explored reusable resource graph models. We learned how to detect deadlock for reusable resources. We started the discussion on consumable resource graph models. Students, I urge you to do the homework that I have set you, and please do all the examples that I showed you during this lecture on a piece of paper by hand so that you understand what I have done. Looking at something does not give you the full idea of that thing until you actually sit down and do it by yourselves. So, please follow these instructions and read the book and note your questions relevant to this lecture and talk about them with me during the online session, and email your suggestions to me if you have any. I hope that this was interesting and easy. Take care. Allah Hafiz.